Closer and closer to the goal that we are trying to achieve in this part of the chapter, which is how to get the potential if you have a certain charge distribution. This is our ultimate goal of this part. And let's review some of the things we showed earlier, that if you get the potential difference between 2 points, it's given by this integral, and it always has one value, same value. Different people can, if you add a constant to the potential at every single point in space, this difference in potential won't change. If you add 5 here and you add 5 here, and you take the difference in potential, the 5 will cancel with the 5, and you still get the same value. So adding a constant to the potential at every point in space, you can do that. It won't affect the physics of the problem, because the difference in potential is the thing that's related directly to the electric field, which if you multiply by Q and divide by Q, you get force over charge. So you're getting forces, which is something that's measurable. So difference in potential is only a certain one value, but you can always add a constant to the potential everywhere and it won't affect the problem. So let's look at what the result we got for a point charge. We showed that the potential for a point charge is kq over r plus a constant. This constant can be any value you want. If you get the potential difference between 2 points, this constant will just cancel out and you get kq over r2 minus kq over r1. So the potential difference between 2 points is always a same value. It only depends on the distance between the charge and point 1, the distance between the charge and point 2. That's all it depends on. It doesn't depend on the particular path you choose to go from point 1 to point 2, or the value of the constant that you add to the potential at every single point in space. So this is then the formula for the potential due to a point charge, kq over r plus a constant. Now here is where people can make a convention or make a convenient choice of a reference of potential. If you put r equal to infinity, then this gives you 0. So the potential is equal to v node. So v node is the value of the potential at infinity. So we're going to make a convenient choice. Let's set v node to be 0. This means that we're choosing the reference of potential where the potential is 0. We're choosing this reference of potential to be at infinity. So for this particular choice, then, we can say that the potential is just kq over r at a point in space. And remember that when we say the potential at a point in space is kq over r, we're still not really saying the potential at a point. We're getting the potential at a point minus the potential at infinity, which we took to be 0. So there's no such thing as potential at a point. You always have to get the potential difference between 2 points. So whenever people say the potential at a point is kq over r, actually what they mean is that the potential at the point minus the potential at infinity is kq over r, and the potential at infinity is taken to be 0. So for this particular choice, that the potential at infinity is taken to be 0, the potential can be given as kq over r, and that means that the potential is symmetric. If you go anywhere, it's spherically symmetric. If you go to any around a point charge on this sphere of any radius, the potential has the same value. I put positive charges give potential values that are red in color, and the color gets weaker as you go far away because the value of r increases, the potential gets weaker. For instance, if you draw a sphere like this sphere around the point charge, the potential, say, at every point on the sphere is 100 volts, for instance. The potential on this sphere at every point is, say, 90 volts, and so on. So the equipotential surfaces for point charges are spheres. What about if the charge is negative? If the charge is negative, then the Q is negative, then the potential values are negative, and the potential is still 0 at infinity, but as you go away from the charge, the potential has negative values. And I put the negative value represented by blue color. So the blue, whenever you have blue, it's negative, and it's more negative when the blue is darker. So for instance, this sphere, if you make a sphere with this radius, the potential everywhere on this sphere is minus 100 volts, for instance. The potential on this sphere is minus 90, and so on. So the equipotential surfaces for point charges are spheres. Now, we got how to get the potential at a point due to one charge. What if you have many charges in space? How would you get the total potential at point P? This is going to be the subject of the next video, and this will then finalize this long process that we've been seeking, how to find the potential for a certain charge distribution.